So here's the picture that I would encourage you to keep in your head. If you have some function, f of x, and we're trying to find the area under f of x between a and b. So we're trying to find this area. The way we express that area is the integral from a to b of f of x dx. And that is the area, or more specifically, it's actually the net area under f of x and above the x-axis. So as long as your function is always above the x-axis, it's kind of what you think it would be. But if things start to be above or below, it gets a little more nitpicky. Welcome. Morning. Thanks. Oh, I can't actually see it. It's all right. Thanks. And then last time we talked about a little bit how you calculate this thing. This feels, let's see. One second, this looks like a little off. So the way we calculate this is using the fundamental theorem of calculus, which says that the integral from a to b of f of x dx can be calculated as, so here's the way I usually write it. Capital F of x evaluated between a and b, where you plug in b first, you plug in a second. But we also then just write it as capital F of b minus capital F of a. The short way of writing the following part is the derivative of capital F is equal to little f. But another way of expressing that is saying, oh yeah, where capital F of x is an antiderivative of little f of x. So that's the gist, right? If we're trying to find the area under some curve between 2 points, this is what we calculate. Let's see here. Oh gosh. Yeah, question.
Is it okay if after we're done with this, we do some integrals of trigonometric functions?
Yeah, definitely.
Do some of them and like some of them were equal to like natural log of something.
Sure, yeah. Let me actually pull up those notes as well. Sorry, I've got problems. I get it later. Okay, so for example, we could say find the area under the curve f of x equal to x squared plus 6x on the interval from 0 to 3. We could draw this. We don't have to draw it, but if you did draw it, it would look like, well, if x is 0, you get 0. If x is 1, you get something. If x is 2, right? So it's looking probably like this. So we're looking at this kind of area here. Right, and there's the rest of the parabola over here. I don't really care about that, but that's kind of the area under this curve. The calculation after some practice becomes very straightforward. If I want to find the area under this curve, I'm calculating the integral from 0 to 3 of x squared plus 6x dx. That's the way. So we anti-differentiate, we get x cubed over 3 plus 6x squared over 2 from 0 to 3. It's usually a good idea to simplify these things before plugging in. So I would probably rewrite this as x cubed over 3 plus 3x squared from 0 to 3. And then we're just going to plug in our limits. It's always the top limit first. It's always the bottom limit second. So we're going to get 3 cubed over 3 plus 3 times 3 squared minus 0 plus 0. Again, I do want to emphasize, please make sure that when you're actually checking when you plug in 0, because a lot of the time you're going to get 0 when you plug in 0, but not always. So here we're going to get 27 over 3 plus 27 minus 0, which is going to be 36. So that's how much area is under that curve. And let's get some other things here. Sorry. Let's look at a couple more examples. Let's say we wanted to find under the curve y equal to e to the x on the interval from 0 to 1. So again, graphically, we can see what's going on here. Here's x equals 0. Here's x equals 1. We're looking for this area here. So we're going to calculate the integral from 0 to 1 of e to the x. It's a very straightforward integral, right? But it's really kind of important to see that, oh yeah, when we do this, we're just doing this process. Here the antiderivative is everyone's favorite antiderivative. It's e to the x, 0 to 1. And then we're going to plug in our limits of integration and get e to the 1 minus e to the 0. And the only thing we should really do at this point is simplify it as e minus 1. We should leave our answer like that. We don't want a decimal approximation. We just want to leave it as is. Or what if we wanted to find the area under f of x equal to cosine of x over 3 on the interval from 0 to pi. And we don't have to draw a picture here, but we could. Cosine of x over 3 looks like cosine of x, except the period's been stretched out. So I know it's maybe been a little while, but here, this function has a period of 2 pi divided by 1/3, which is going to be 6 pi. So the cosine function on this very long period starts at the top and then goes to 0 and then to the bottom and then back to the middle and then back to the top. So it would look like this, where that period is 6 pi. So in the middle is 3 pi. That's like 3/2 pi. So we're really just looking at like this little bit here. We're trying to find that area. Again, you could totally answer this question without drawing a picture, right? It's good to draw pictures to see, but not particularly necessary. So here, the area we're looking for is going to be the integral from 0 to pi of cosine of x over 3. Okay, antiderivative cosine of x over 3 is going to be, is it positive or negative sign? Positive sign. But what else do we need besides sine of x over 3? Not a tangent, so I need a constant, right? If I took the derivative of this, I would get cosine of x over 3 times 1/3. But I don't have a 1/3 there, so I need to divide by 1/3 or multiply by 3 to account for that. This is again one of those examples of what I call a mini u substitution, where if the derivative would make you multiply by a constant, the antiderivative is going to make you divide by that same constant. So here we're going to get 3 sine of x over 3 from 0 to pi. And then we plug in. We get 3 times sine of pi over 3 minus 3 times sine of 0 over 3. Sine of 0 is 0. And sine of pi over 3 is something we're supposed to know. It's the square root of 3 over 2. So continuing in the direction of thinking about area under the curve as an integral, or the integral as the area under the curve, we can ask some questions for functions we don't actually know how to anti-differentiate. One of them we could figure out, but we don't typically do it that way. Another one, it's less straightforward. So what if I wanted to find, or I wanted you to calculate the following integral? The integral from -1 to 7 of the absolute value of 2x minus 6. So there is a way you can do this actually through anti-differentiation, but it would require breaking this up into two separate intervals. The better way to deal with an absolute value, I should say, for an absolute value of a linear function. Right, so if that was like x squared minus 9 in there in the absolute value, we would have to break it up. But for something like this, we can say, well, I can draw a picture. I'm going from -1 to +7. And I know that this absolute value of a linear thing looks like a V shape, right? And the bottom of the V is when the insides are equal to 0. So the quote unquote bottom of my V is going to be when 2x minus 6 equals 0. Or in other words, when x is equal to 3. So there's the bottom of your V there. And then it's just kind of look like this. And I could totally find what that point is right there by plugging 7 into the function. And I could totally find what that point is right there by plugging -1 into the function. I might have made it look like they're the same height. That might not actually be true, right? My picture isn't perfect. It doesn't need to be perfect. So if we plug in 7 to the absolute value function, so again, for y equal to the absolute value of 2x minus 6, if x equals 7, we're going to get a y value of the absolute value of 2 times 7 minus 6, which is 8. If we plug in x equal to -1, we get a y value of, I actually do have the same height, it happened to be the same, of 2 times -1 minus 6, which is the absolute value of -8, which is 8. So then I can find the area under the curve, which is what the interval is asking us for. I should say, which is what the definite interval is asking us for. Stand, silly thing. Okay, sure. All right. My pen bag keeps falling over. There's too many pens in the problem. Okay, fine. So we can find the area under this curve. Well, I know what that shape is. That's a triangle. That triangle has an area of 1/2 base times height, where the base is 4 and the height is 8. And that's gonna be 1/2 times 32, which is 16. And then we can do the same thing for the other triangle, which happens to have the same base and height, right? This base is 4, this height is 8. This triangle has an area also of 1/2 times 4 times 8, which is also 16. So this integral, this area under the curve, is exactly that plus that, which is 32. So when we're trying to find the area under an absolute value function, it is often most easily done by just writing the absolute value function, or I should say by drawing the absolute value function and then seeing that the area under the curve is just triangles added together. Let's see, I feel like there's something else I want to do there. I should point out, because it might come up later on, you could also calculate this by breaking it up. You could say, well, this line right here really is the line y equals 2x minus 6. And this portion of the line right here really is y equal to negative 2x minus 6. And so if you wanted to, instead of doing it the way we just did it, you could break it up as two intervals. The interval from -1 to 3 of negative 2x minus 6 plus the integral from 3 to 7 of 2x minus 6. That would also work out just fine, but it's a little more computationally heavy. It is a method we have to use if we want to calculate something like the following. So what if instead we said, find the following? Find the integral from, what do I want to do here? Sure. From -2 to 4 of the absolute value of 4 minus x squared. This one is going to require a little more effort. Now, the thing I would say about this is it's still a good idea to draw a picture. And this one's kind of weird. So let's first just draw y equal to 4 minus x squared, which is parabola flipped over, shifted up. It looks like the following. Has intercepts of a y-intercept of 4, x-intercepts of plus or minus 2. So it's going to look kind of like this. Now, when I think about an absolute value, I think about kind of the defining feature being that when I take the absolute value of something, all the results are non-negative. I take the absolute value of the value, I get something positive, or I could get 0. So meaning if I'm graphing an absolute value of something, all the negative things have to kind of flip over and become positive. So the way I'm going to graph y equal to the absolute value of 4 minus x squared is the part that was positive is going to stay positive. So this part here, like that, is going to stay as it was. But then these parts here are going to flip over and do this kind of thing. So it's going to look like this. Kind of weird, but not that weird. So then if I want to find the area under the curve from -2 to 4, so here's -2, here's 2, 3, 4. I guess it drops a little bit further right. Here I really do have to break it up. So I have to say, well, the integral from -2 to 4 of the absolute value of 4 minus x squared. From -2 to 2, I just get the insides, right? Because from -2 to 2, 4 minus x squared is positive, or I should say non-negative, right? If I plug in something like 1, 4 minus 1 squared is a positive number, so I don't have to change the sign of it. So it's just that. The integral from -2 to 2 of 4 minus x squared dx. But from 2 to 4, it's no longer 4 minus x squared, it's the negative of 4 minus x squared. And I suppose I should say maybe a tiny bit more about this. This is speaking to the fact that when you take the absolute value of something, the absolute value of 4 minus x squared is equal to, I'm just going to say this very, very broadly. It's equal to the stuff you have inside if the stuff you have inside is positive. Right? Take the absolute value of a positive number, you get back the same thing you started with. But if the stuff you have inside is negative, the way you change it to being positive is by multiplying it by -1. So when 4 minus x squared is positive, which is here, right, between -2 and 2, we don't change it. But when 4 minus x squared is negative, so over here when x is bigger than 2, or over here when x is less than -2, then 4 minus x squared would be negative, and we have to flip its sign to make it positive. So then we can calculate this without too much trouble. We're going to get, well, that's a good time to kind of see a thing. So I'm going to do something that I'll explain in a minute here. This integral, a lot of people would rewrite in the following way. They would say it's 2 times the integral from 0 to 2 of 4 minus x squared. And so you might see this in a book like in the solution, but what's going on? What happened? So what they did was they said, well, I'm trying to find for this part here, that area there. But since that function, 4 minus x squared, at least on that particular part there, whoops, is symmetrical about the x-axis, or sorry, about the y-axis, also known as being an even function, you can take just the right half of it, which is the integral from 0 to 2, and then double it. Very, very common tactic. And we'll say it again in just a minute, but I just want to point out that's something people do a lot, and you'll see in books for sure. This other one, I'm just going to write as the integral from 2 to 4, and I'm going to distribute the minus sign and get -4 plus x squared. So then calculating things, we have 2 times, okay, the antiderivative of 4 minus x squared is 4x minus x cubed over 3 from 0 to 2. Oh, sorry, I forgot the chat disappeared. Not that anyone's writing anything, but it's good to keep it up there. And then we're going to have plus the antiderivative of this, that's going to be a -4x plus x cubed over 3 from 2 to 4. And then we'll plug in the limits of integration. We'll get 2 times, so when I plug in 2, I'm going to get 8 minus 8/3. And when I plug in 0, I'm going to get 0 minus 0. Plus, over here, when I plug in 4, I'm going to get -4 times 4 is -16. Plus 4 cubed over 3 is 64 over 3. Minus, when I plug in 2, I'm going to get a -8 plus an 8/3. And then we could calculate this and get a number. I don't really want to do it though, because I'm feeling like I don't have a lot of room to finish the problem. I suppose we could do it up here. So let's see, 8 minus 8/3. So if I was doing this, I would probably kind of simplify this by not putting those together. I would say I have 2 times 8 is 16. 2 times -8/3 is -16/3. And then 0, and then -16 plus 64/3 plus 8 minus 8/3. So putting this all together, the 16s cancel, and I end up getting 8, and then -16/3 minus 8/3 plus 64/3 is going to be 64 minus 16 minus 8 all over 3. And that's going to equal 8 plus 64 minus 16 is 48, minus 8 is 40/3. Or if you like, you could get a common denominator and say it's 64/3. Again, that's not the super important part of the process, but it is part of the process. So absolute values, kind of interesting. Usually though, most people aren't making you do this. Most people are asking you a question like the previous question where you can just draw a picture and find the answer relatively straightforwardly. There is one other type of function that often comes up where we really, really don't want to anti-differentiate it. And that is the following. If I wanted to find, say, the integral from -4 to 0 of the square root of 16 minus x squared dx. So we don't in this class ever learn how to anti-differentiate this function. There is a way to anti-differentiate it. It requires a process called trigonometric substitution, which is not taught in the 16 series, which is fine. You know, it's kind of a big pain in the butt, but it's also not. So what we do here is say, well, what does this function actually look like? And you might not recognize it as it's written. But if we do a little bit of manipulation, like squaring both sides and adding x squared over to the left, we get x squared plus y squared equal to 16. And what's the graph of that equation? It's a circle with a center at the origin and a radius of 4. Now, the only difference between this, where the center is 0, 0, and the radius is 4, the only difference between this and this is that in this second equation, you get the full circle. X and y can both be positive or negative. But in this first expression here, you only get the top half of the circle because y can't be negative if you're taking if y is equal to the square root of something. So here we have to note that y is greater than or equal to 0. So we only get the top half of the circle or the semicircle. So this looks like a semicircle with radius 4. And we're trying to find the area under this curve from -4 to 0. And I really should say from x equals -4 to x equals 0. So we're starting here and we're ending here. And we're finding all of the area under the curve. Well, great. I know how to find the area of 1/4 of a circle. That area is going to be 1/4 pi times the radius squared. Because the area of a circle is pi r squared. So the area of 1/4 of it is 1/4 pi r squared. And that's going to end up being 4 pi. In a similar way, you all could find the following. In fact, I'm going to have you do. So find the integral from -3 to 3 of the square root of 9 minus x squared. I'll let you work on that for a minute. I would encourage you to draw the picture. Very possibly, yeah. Okay. So this one is a circle of radius 3, but it's the top half of it. But in contrast to the previous problem, it's the entire top half because we are going from -3 to +3. So in this case, the integral is going to equal 1/2 pi times your radius squared instead of 1/4 because it's a whole half instead of the whole quarter. So I write that as 9 pi over 2. So those are the two kind of specific types of integrals where you're kind of expected to just draw a picture and then find the area that way instead of trying to calculate the antiderivative. Yeah. So let's talk about a few properties of integrals. I promise we'll definitely get to the trig. I'm circling back around to trig, I promise. But there's just a couple of integral properties I want you all to be aware of because I've seen your homework assignments and they are coming up. So one property that comes up frequently is the following. And I've actually kind of used it already today, but I want to say it more specifically. So I'm going to write this as the following. The integral from a to b of some function is equal to the integral from a to c of that same function plus the integral from c to b of that same function. In other words, if you have an integral, some definite integral from a to b, you can break it up at any point in between. Actually, you don't even need the in-between part, but usually we like to think of it as being in between. So here's what I mean. If I have a function and finding the area under that curve from A to B. Well, if I break it up at some point C, I think it's not too hard to tell that this area here, which is the area from A to C of f of x dx, and this area here, which is the area from C to B of f of x, those add up to the area that's the total, right? That entire area is the integral from A to B of f of x dx. And those are definitely equal. The red area plus the green area equals the total area. So you can break up an integral at any point in between the two endpoints. And in fact, so usually we think about the point C being between A and B, but I'll point out C actually doesn't have to be in between A and B. It's nice when it is because it makes more sense visually, but it works no matter where you put C. So C could have been like way over here or way over here, and it still actually works out just fine. And that actually has to do with one of the other properties of integrals. So a couple other properties that I want you to be aware of. I really should say properties of definite integrals. That's kind of what we're exploring right now. There's like 3 more things I want you to know. And they are the following. So I'm trying to keep the page here. So one of those things is that the integral from A to B of f of x dx is equal to the negative of the integral from B to A of f of x dx. So if you happen to get this, if you want to change the order that the limits are in because you don't like the way they're ordered, you end up changing the sign of the integral. Another way of reading this, which seems kind of weird, is essentially if you integrate in the backwards direction. So if you integrate from right to left, your area gets counted the opposite way. So just for example, right, if I was calculating the integral from like say 3 to 0 of x squared dx, right, and that x squared looks like this. If I'm finding that, well, I'm going to end up getting a negative value because I'm going to get x cubed over 3 from 3 to 0, and we always plug in the top limit first minus the bottom limit second. And that's going to end up being negative 27 over 3. We could have rewritten it as negative the integral from 0 to 3 of x squared dx. And we would have gotten the same thing. So when you have your limits out of order, you can change them, you just have to change the sign. And sometimes that's really convenient because sometimes you have an integral where you have a negative sign and the limits are looking wrong, meaning not the usual order, and you can flip them and change the sign. It's kind of nice. 2 other properties that come up quite frequently. One of them is the following. The integral from negative a to a of an odd function is equal to 0. There are lots of good examples of this. Some pretty standard ones are the following. The integral from negative 2 to 2 of x cubed is equal to 0. We can think about this graphically. X cubed is never when I'm good at drawing. It's like it's one of my biggest challenges. Let's see. Sure, that looks all right. So if we go from say negative 2 to positive 2, what's going to happen with those areas? Right, the area over here is going to get counted as positive. The area over here is going to get counted as negative. And since they match because the function's odd, they're going to cancel out. You could also calculate it, right? You could say that's going to equal x to the 4th over 4 from -2 to 2, you're going to get 2 to the 4th over 4 minus -2 to the 4th over 4. But that's 16 over 4 minus 16 over 4, which is 0. Now, the reason this is sometimes useful is because someone might ask you something terrible. Someone might ask you, come on, page. Someone might say, find the integral from -5 to 5 of x squared sine of x over x to the 8th plus 9. And the problem with that is, I don't know how to anti-differentiate that. It's almost definitely not anti-differentiable. But the point is, you don't have to be able to anti-differentiate it. So if you see that these limits of integration are opposite numbers, that's a clue. And we should check to see, is the function odd? Well, we have to check. So if we call our function f of x, and it's x squared times sine of x over x to the 8th plus 9, the way we check to see if a function's odd is we have to check, is f of -x equal to -f of x? And there's one kind of important fact we need to remember here. Trig functions, every trig function is either odd or even. Specifically, cosine and secant, its reciprocal, are both even. If you think about the cosine function, it has that even symmetry. It's reflective around the y-axis. Every other trig function is odd. So sine is an odd function. Specifically, right, we draw a sine. It looks like that, right? Sine is definitely an odd function. It's got that rotational symmetry, or if you rotate it around the origin 180 degrees, it looks the same as it did before. So it's certainly true that sine is an odd function, that sine of -x is equal to negative sine of x, because sine is odd. So that's going to help us do this. If I look at f of -x here, f of -x is -x quantity squared times sine of -x over -x to the 8th, plus 9. Negative things, well, -x squared is just -x times -x, which is positive x squared. Or you can really just say -x to an even power is going to be positive x to the same even power. So we're going to get x squared. And then sine of -x is negative sine of x over x to the 8th plus 9. Oh, look, that's exactly what negative f of x is equal to. So those are equal, which means the function's odd, which means the integral is 0. So if you're using this fact that the integral from negative number to positive same number of some odd function is odd, usually you're going to be required to actually show that the function's odd. Unless it's unless it's like x cubed, right? If it's x cubed, yeah, okay, it's odd. But if something more complicated like this, there's probably an expectation there that you show it's odd. The other last integral property for now that is less cool, but is still cool, is that the integral from -a to a of an even function, which again, I cited this one earlier, is equal to double the integral from 0 to a of the same even function. And that's just because we're essentially cutting the area in half and then doubling it. So for example, the integral from -3 to 3 of 16 minus x squared is going to probably be easier to deal with if we cut it in half. So we go from 0 to 3, and then we double it. Really, the point of this is just to make the plugging in part less terrible. It's a lot nicer to plug in 3 and then subtract and plug in 0 than it is to plug in 3 and then subtract and plug in -3. There's a lot of like bookkeeping with negative signs there that it can be easy to make a mistake and get the wrong thing happening. So that's mostly where we use that. I don't really want to say more about it. Let me see here. Let me look at one more thing. What time is it? That's not, what time is it? Okay. Let me do one more definite integral and then we'll do some trig functions. So another thing that we often do with definite integrals, and we did, I think, one of these last time, is when we find the area between two curves. So I want to find the area between, say, f of x equal to x squared minus 4x and g of x equal to x. And although, again, I say this all the time, you don't typically have to draw a picture, but it's also kind of nice to draw a picture. So let's draw a picture. X squared minus 4x, I know is a parabola. I know it opens upwards. And if I factor it, I can see that the intercepts are going to be 0 and 4. That's going to look something like this. And then let's do y equals x over here. Y equals x looks like this. So obviously, these intersect at the origin, right? They both go through the origin, so that makes it easy. And then there's some other point of intersection up here. And we're trying to find this area. And so what we're going to do is so the end result is we're going to integrate. We're going to integrate the top function minus the bottom function. But the rationale for this, and I do think it's good to think of it this way, is you're essentially adding up a bunch of little rectangles. This idea does come back when we start talking about volumes of revolution, which is why we're kind of talking about it. So we are, quote unquote, adding up a bunch of rectangles. So the idea is, what's the area of one of these rectangles? Well, if I look at that rectangle right there, the area of this rectangle is very, very generally base times height. The base, well, the thing about this is the rectangles are getting thinner and thinner and thinner and thinner and thinner to get a better and better approximation. We'll talk about approximating a little bit later. Actually, there is a section about like we approximate using rectangles. But for now, we're just kind of thinking, I'm going to let the width of the rectangles get very, very small. And we're going to call that width dx for a small, small, small change in x. So our base is actually dx. If you're doing this approximation thing later, we often call it delta x for a change in x. Delta x and dx are very, very related to each other. And then the height is actually what I want to focus more on here. The height of this rectangle, well, it changes, right, as we go from left to right. But the height of this rectangle is always the top value minus the bottom value. The height of that rectangle is the top function minus the bottom function. And then if we're going to add up all the rectangles, to add them all up, we're going to integrate the base times the height from the left point of intersection to the right point of intersection. So that's what we're calculating when we do this. Now the process becomes much more straightforward. We don't write this out every time. We're going to say, okay, I'm going to look at my function, my curves, I'm going to find out where they intersect. And to find where they intersect, we set them equal to each other. So we're going to set x squared minus 4x equal to x. I'm going to bring the x over to the left since I'm going to get x squared minus 5x equal to 0. Factor. and we get x equal to 0 and x equal to 5. So my integral is going to look like the integral from 0 to 5 of the top function minus the bottom function. That's my height, dx. Now, I drew it, so I knew which one was on top just by looking at it. But if we didn't draw the function, how would you know which one was on top or which one was higher up? Well, one way of doing it is say, well, these two functions intersect at 0 and 5, meaning they have the same values at 0 and 5, right? If you look at f of 0, it's 0, and g of 0 is 0. And if you look at f of 5, it's going to be 25 minus 20, which is 5, and g of 5 is definitely 5. But those are the only places where they're equal. So anywhere between 0 and 5, since they don't cross each other again, one of them always has to be larger. And the way you can figure out which one's larger is pick a test point. Pick any point between 0 and 5. I'm going to pick 1. So if I pick x equal to 1, I can see that g of 1 is 1, and f of 1 is 1 minus 4, which is negative 3. So clearly, g of x equal to x is the larger function on that interval. So if you don't want to draw it or can't draw it because it's super funky looking, you can always test a point in between the endpoints and figure out which function's bigger that way. So I know it's going to be x minus x squared minus 4x. There's your top. There's your bottom. And then we're going to simplify. We're going to do the integral of x minus x squared minus a minus 4x. So I got x plus 4x, which is 5x minus x squared dx. From 0 to 5, we anti-differentiate. We get 5x squared over 2 minus x cubed over 3 from 0 to 5. When I plug in 5, I'm going to get 5 times 5 squared, which is 125 over 2 minus 5 cubed is also 125 over 3. And then I plug in 0, I get minus a 0 minus 0. Now, here's that. I feel like I've referred to this trick before. If you see two fractions where the numerator happens to be some large number that's the same, right? Like I have something over 2 minus something over 3, factor out that large number. I'm going to make this 125 times 1/2 minus 1/3. To me, that feels a lot easier to deal with. That's going to be 125 times 3/6 minus 2/6, which is going to be 125 times 1/6, or 125 over 6. So that's how I would find the area between these two curves. Find where they intersect, figure out which one's the larger one, which one's the smaller one, do the larger one minus the smaller one, and find the integral over that interval. Yeah?
Where did that 5 come?
The 5 came from setting the two functions equal to each other. So when I set x squared minus 4x equal to x, I ended up getting x equal to 0 and x equal to 5. And that's typically how we find the limits of integration. So specifically, if you're asked to find the area between two curves or bounded by two curves, you have to find where the curves intersect each other. It feels like it might be worth doing one. I know I said trig stuff next. Let me do one more example, and then I promise. Swear, I cross my heart. Okay, so one more example. Let's say we wanted to find the area between the curves. Now I'm having trouble remembering what we've done before, but let's just make something up. Let's say we have y equal to, this is where I always make the dumb error. So let me make sure I don't do something silly here. Say we have y equal to the square root of, sure, do that. That's always feels so boring. That's fine. Okay. Y equal to the square root of 3x and y equal to x. Sure, that'll be fine. Although not particularly exciting, but it's okay. So here's y equal to x. And y equal to the square root of 3x looks kind of like this. It looks like the square root function would kind of scrunched horizontally. Now again, I'm drawing these from experience, right? I know what these functions look like because I've seen them a lot. But we could also first find the information and then draw them, or at least do a better job of drawing them if we knew more information. So pretending like we didn't just do that, I'm going to find where these functions intersect. So I'm going to set the square root of 3x equal to x to find the points of intersection. I suppose instead of just covering this up awkwardly with my hand, I could do this. There, now you can't see it. That feels not as good here. Let me do this. There. Now it's really not there for now. That's there. Finally, I have anything to cover something here. How about that? Yeah, that's good. All right. So, okay, it's gone. It's disappeared. It's from our mind. Oh, and sorry. Laptop. Okay, good. You can see the stuff too. All right. So, if I'm setting square root of 3x equal to x, how am I going to solve that? What seems like a good first step? Yeah. Square both sides, get 3x equal to x squared, and then in fact, bring everything to the left or the right. 3x minus x squared equals 0. X times 3 minus x equals 0. So we're getting x equal to 0 and x equal to 3. Those are both solutions in this case, but I will warn you, occasionally when you square both sides of an equation, sometimes you do get extra or extraneous solutions. So we should check them back in the original equation. If you plug back in 0, square root of 0 equals 0, check. If you plug back in 3, square root of 9 equals 3, yeah, check. So we're fine here, but just as a word of warning, if you do square both sides of an equation, you can get fake solutions. All right. So, I was gonna do one more thing. Oh well. So if I check, say if I check a value between 0 and 3, like check, say x equal to 1, what function is bigger? Well, the square root of 3 times 1 is the square root of 3, and I should say right, y equal to that, versus y equal to x is going to give me just y equal to 1. So what's bigger, the square root of 3 or 1? So the way square roots always feel kind of hard, but not if you think about it a little bit. So let me ask you a different question, totally off to the side. What's bigger, the square root of 7 or 2? Right, but how do we know without a calculator, right? You might know that the square root of 7 is 2 point something, but the way I think about it is write them both as square roots. 2 is the square root of what? Right. And now it's easy to see, oh yeah, the square root of 7 is bigger than the square root of 4. Similarly here, 1 is the square root of 1. And so now we can be like, oh yeah, the square root of 3 is definitely bigger than the square root of 1. Because the square root function is an increasing function. If you think about the graph of the square root function, it's getting bigger and bigger and bigger as you go from left to right. So as long as your input's larger, your output is also larger. So this is definitely the bigger one. Which means to calculate the area, we're going to do the integral from the left-hand limit to the right-hand limit, which is from 0 to 3, of the larger function, square root of 3x, minus the smaller function, x. This one is interesting. This is where you have to be a little extra careful. I'm going to rewrite my integral as the integral from 0 to 3. I'm going to write the square root of 3x as the square root of 3 times the square root of x. Because it is, and I'd really rather not do a u substitution. So now, the antiderivative of a constant times the square root of x, that constant hangs out, and the antiderivative of x to the 1/2 is x to the 3/2 times 2/3. So it is true that the square root of a times b is equal to the square root of a times the square root of b, as long as a and b are both positive. If a or b are, if either one of them is negative, you have issues. That's what I'm doing there. I'm breaking the square root of 3x as the square root of 3 times the square root of x. And then the square root of 3 is a constant. It's like 1.7-ish. It's staying out in front. And then we're anti-differentiating the square root of x. And then the antiderivative of x is x squared over 2 from 0 to 3. The numbers aren't nice here. I probably should have picked 4x instead of 3x. Oh, well. We're going to plug in 3 and we're going to get the square root of 3 times 2/3 times 3 to the 3/2 power minus 3 squared over 2 minus 0 minus 0. Now, this actually is nicer than it looks. What's another way of writing the square? So normally I would leave this as is. Especially if it was a test, I'd be like, yeah, I'm done. I'm gonna stop there. If I have time at the end, I'll come back and try and work on it to make it simpler, because usually they say you simplify your answers. But on a test, I'm stopping there. I'm getting most of the credit, unless your teacher's insane and doesn't get partial credit. But typically most people get partial credit. But I should point out here that the square root of 3, I could rewrite that as 3 to the 1/2 power. And then I will notice that I have a 3 to the 1/2 times 3 to the 3/2. And when you multiply those together, what do you do with the powers? And what's 1/2 plus 3/2? 2. So this ends up simplifying rather nicely. It's going to be 3 squared times 2/3 minus 3 squared over 2. That's going to end up being, cancel a 3 here and a 3 here, 6 minus 9/2, or 6 minus 4.5, which is 1.5. Or 3/2 if you prefer. But this one does actually work out to be not so terrible, even though it looked like it was going to be terrible. All right, let's do some trig. Of course, I was gonna pull up some trig examples and then I didn't because I got distracted. Sorry, I've got lots of trig examples though. One sec. So I've looked at your, well, actually, whose class are you in? Out of curiosity. Gentleman in the white hoodie whose name I don't know. Whose class are you in? Okay. So I've looked at her homework semester and I haven't seen any. So there's kind of 2 varieties of trig questions. One are what I'll call the not too terrible ones, and then there's the more terrible ones. Okay. Sure. And I did, and I haven't, unfortunately, okay. So we can definitely talk about. Does it, well, are they midterms or are they like her short tests? Yeah, so you probably have one like, you have one like every 2 weeks, I think. Yeah. Because she's trying to, I mean, she really does, like, I think she's a great teacher. She really does care about the students and the learning experience. And she's trying to test relatively frequently with not as like high stakes tests. But I understand from the student perspective, it might not always feel that way. Yeah. So let's look at some examples. Let's say we wanted to do, say, the integral of, let's start easy. Sine x times cosine squared x dx. Is that easy? Is that terrible? No, that's fine. Okay. So when you see sines and cosines, typically you're going to let u be one of those trig functions and not including any power. So you're just going to pick either u equal to sine or u equal to cosine. And there's kind of, depending on what your powers look like, there are things that work and things that don't. Here, I don't want to pick u equal to sine of x. The reason being, my du is cosine of x dx, but I have a cosine squared. And so after I let u be that and du takes care of one of the cosines, there's still an extra cosine left over. That's the wrong choice. Instead, we're going to let u equal cosine x. And then your du is going to be negative sine of x times dx. So I'm going to say negative du equals positive sine of x times dx. And now look, things are going to work out all right. My sine of x dx, that's going to come together. I should really say that's going to multiply together because they are multiplied together to become my negative du. So then this integral is going to become the integral of a negative du times, instead of cosine squared, now I'm going to have u squared. I would put the negative sign on the outside. And then the antiderivative of u squared is going to be u cubed over 3 plus c. And then we plug back in what u is, and we get negative cosine cubed x over 3 plus c. And I will say very generally, if at least one of your trig functions is raised to an odd power, you want to let u be the one that's, I should say, if you have one odd and one even, you really want to let u equal the one that's raised to an even power. So let me give you another example. Let's say we want to do the integral of, sure, sine squared x times cosine cubed x dx. So there's one choice here that's really going to work. There's one choice here that really isn't going to work. And the choice here that is going to work is letting u equal to sine of x. And so then your du is going to be your du is going to be cosine x dx. Now, why is this a choice that's going to work? Well, it doesn't actually look so great so far. So what I'm going to do is I'm going to say, well, I have a cosine x dx. I need to break that off. Typically, especially with trig functions, I usually like to write this as this. So I took my cosine cubed x and I stole one of the cosines from it to take care of my du issue. So my du being equal to cosine x dx, there's my cosine x dx, which is du. And then sine squared x, well, u is equal to sine, so that sine squared is going to become u squared. And then what about the cosine squared? It's not u squared because u is sine. So this is where you have to use a trig identity. So it's true that sine squared x plus cosine squared x equals 1. That is a trig identity that you should all be aware of. And then if we solve for cosine squared, we get cosine squared x equal to 1 minus sine squared x. But sine is equal to u. So this is equal to 1 minus u squared. We distribute the u squared to the 1 minus u squared and get the integral of u squared minus u to the 4th. That's going to be u cubed over 3 minus u to the 5th over 5 plus c. And then we plug back in u equal to sine. We get sine cubed x over 3 minus sine to the 5th x over 5 plus c. So here's the idea with these problems. And I know we only have like 6 minutes left, but typically when you have powers of sines and cosines, or we'll see powers of secants and tangents, the idea is you want to make a choice for u so that after you've dealt with du, the thing that you did not choose for u, there's an even number of them left over so you can use a trig identity. So I chose u equal to sine here because once I dealt with du being cosine, there was an even number of cosine left over. And so I could change that cosine squared into a trig identity using sine squared. In a similar way, if we had to say do the integral of cosine to the 5th x times sine cubed x dx. Excuse me. There's actually no wrong choice for you here, but there's a better choice for you. So let me show you two things. One way of doing this. This is not the way we're going to do it, but let me show you how this could work. So if we let u equal sine x, our du would be cosine x dx. I would break off one of the cosine x's from cosine to the 5th, rewrite this as the integral of cosine to the 4th x times sine cubed x times cosine x dx. The cosine x dx is my du. Sine cubed is going to be u cubed. And then I have to use my trig identity again. My trig identity is sine squared x plus cosine squared x equals 1. It's not sine to the fourth x plus cosine to the fourth. You can't like add whatever power you want and make it work. So we're going to solve for cosine squared. So cosine squared x equals 1 minus sine squared x, which is going to be 1 minus u squared, because u is sine in this particular problem, right? We chose it right there. And then we have to square both sides. So this is going to be 1 minus u squared squared. It's totally doable. Right? You multiply that out, you distribute the u cubed, and you integrate this thing. But there's a better choice. If both powers are odd, you always pick u to be the one to the higher power. It's going to mean there's less left over of the other one. So instead, pick u equal to cosine x. Then your du is going to be negative sine x dx. We're going to change it to a negative du equal to positive sine of x dx. And then I'm going to rewrite my integral as the integral of cosine to the fifth x times sine squared x times sine x dx. My sine x dx is going to be negative du. My cosine to the fifth x is going to be u to the fifth. And using this trig identity here, I'm going to have sine squared x equal to 1 minus cosine squared x, which in this version will be 1 minus u squared. But since I don't have a leftover sine to the fourth, I don't have to like square both sides. I can just plug in a 1 minus u squared right there. So it's a little bit easier to do it that way. So then we're going to get the integral of u to the fifth times 1 minus u squared times a negative du. And typically, no, maybe. So here's what I would honestly do. I would write this as negative the integral of u to the fifth minus u to the seventh. And then I would actually distribute the minus sign and have the integral of negative u to the fifth plus u to the seventh. And then I would have negative u to the sixth over 6 plus u to the eighth over 8 plus c. And then plugging back in cosine, I'd have negative cosine to the sixth x over 6 plus cosine to the eighth x over 8. So that's kind of the gist with these problems is you're making a choice for u so that the leftovers after you've dealt with du are to an even power so you can use a trig identity. Let me show you one with secants and tangents. Let's see. So I should point out for both of these, there is one choice where it doesn't work, meaning we can't do this. We can't do a u sub for the integral of say like sine squared x times cosine squared x. In this case, you have to use a terrible trig identity. You have to rewrite this using sine squared x equal to 1 minus cosine of 2x over 2 and cosine squared x equal to 1 plus cosine 2x over 2. Before we go through the terribleness of doing this, I will actually make sure you're going to see that. Like, I don't want to spend time doing this if you're not actually going to see it. In a similar way, you can't do a u sub for something like secant cubed x times tangent squared x. It doesn't work for this. And this one is especially terrible, but we're going to wait on these because they might not actually come up. Well, let's look at, sure. I'll throw one more at you and then we'll be done. Let's say we want to look at the integral of secant cubed x tangent cubed x. We want, let's actually see it. So we want to pick u either equal to secant or tangent. But here's what we want to happen. If we pick u equal to secant, then we want the du to after we've taken away what's from the du, we want the leftover other function. So if we pick u equal to secant, we want the leftover amount of tangent to be to an even power. So here are our possible choices. We could pick u equal to tangent, or we could pick u equal to secant. If u equals tangent, what's my du? Yeah. So let me ask you, after I pull out the du, is there an even amount of not tangent left over? No, right? If I pulled out the du, this would become the integral of secant x tangent cubed x times secant squared x dx. And there is a odd amount of the not u choice left over. Right, so you're always looking at what you didn't pick for u and it's asking, is there an even amount of it left over? So that's not the right choice. We don't want to do that. It's not going to work out. If you need to go, feel free to go, by the way. I'm almost done now. On the other hand, if we let u equal secant, our du is secant x tangent x dx. And if we pull out the du part, we're going to get the integral of secant squared x tangent squared x times secant x tangent x dx. There's my du. I should say there's a. So now the thing I didn't pick for u, so I picked u equal to secant. The thing I didn't pick, which was tangent, there is an even amount of it left over, which is good because then we can use a trig identity. The trig identity, so you'll never forget this. The trig identity is prepared to have your ears murdered. I tan and get sexy. I tan and get sexy. You cannot forget. A student taught me that one time. I was like, oh, you can never forget that. It's emblazoned upon your mind forever and ever and ever. But what that means for us is we can replace tangent squared x with secant squared x minus 1. Or in this case, tangent squared x with u squared minus 1. So this becomes our u squared minus 1, and this is just u squared. So this is the reason why we want the non-u choice to have an even amount left over. Because if there's an even amount left over, you can always use one of these trig identities to replace it with the other trig function. So this is going to end up being the integral of u squared times u squared minus 1 du, which is the integral of u to the 4th minus u squared du, which is u to the 5th over 5 minus u cubed over 3 plus c, which is going to be secant to the 5th x over 5 minus secant cubed x over 3 plus c.